Guys, welcome. So, I'll be doing an experiment where I'll be showing you voltage, current, and resistance characteristics within electronic circuit. Right? So, this presentation brought to you by the Vigilant Society of Engineers. You may visit us at www.vigilantsocietyofengineers.com for more information as it relates to these circuits and in particular codes on electrical systems. Right? But we're just doing an experiment because we want to get the knowledge out from engineers, prospects, and those who are practicing within the field. All right. Now, for some person, this may be, no new news, but then, this is just something that is going to help remind you the behavioral characteristics of voltage, current, and resistance. All right. So we're going to lay out a schematic diagram. We're going to put in some resistors. We're going to put in some voltage supplies, and we want to also demonstrate using a real-time circuit with the same resistors and the value of the voltage supply, and we're going to compare and see what the experimental value is as it opposed to the value within the circuit, right? So that value is something that we're going to also calculate, right? So I'm going to calculate that value and I'm going to measure that value using real circuit on a breadboard. All right. So bear in mind. So then the schematic layout of a series parallel circuit, right, is somewhat can be highlighted, where we have a resistor in series against two other resistors that is merged in parallel. All right. So observing this diagram, we have one side of the branch circuit, which is a series, and the other side, which is a parallel series combination. All right. So we have 100 ohms resistors and a 200 ohms resistance on the parallel side of the circuit, which is also in series. So this section on the right side is a series parallel section, and it's met upon a 220 ohms resistor, which is in series with the series parallel combination. All right, so I'm going to look at this circuit and I'm going to break it down, and we're going to calculate the voltage across each resistor and the current that is flowing in them either, right? And then we're going to make sure, before we get into that, we calculate the total resistance within the circuit. All right. So step by step, we're going to break it down so that you guys understand how to do the calculation. All right. So here goes. So now, if I'm calculating the total resistance within this circuit, I need to break it down in different sections. So if I start from my right, I have a series component or combination of 100 ohms and 200 ohms. And then going to my left, I have another 100 ohms resistor, which is in parallel with the series section. All right. So on the right side, we have a series parallel circuit. All right. And then now, if we should add the total value of the series parallel portion to the series circuit met upon the first supply voltage, then that would have give us the combination or the total that we're looking for. All right, so let's isolate one section. We're gonna add 100 ohms with 220 ohms because that is series. All right, so judging by our equation, RT equal 220 ohms plus 100 ohms slash 220 ohms plus 100 ohms. All right, so observing this equation, you can see exactly what we're about to do. All right, so all I'm going to do is just break it down all the way down to find the total resistance. All right, so if we should find the current now, we're just going to take the total resistance within the circuit and divide it by the voltage. So the current within the circuit, as determined, would have been 0.017 amps. Now, let us further analyze the circuit. And as earlier, we want to tell you that objectively, just want to look at the voltage within the circuit. And we're going to make mention to the current, of course, because the current is important to determine the value of the voltage drop across each one of the resistors. Right? So when we analyze the voltage within the circuit, we just want to see how much value of the voltage is observed or dropped across each one of the resistors. So if we're supplied by 5 volts, then we may have to understand that they're going to have a voltage drop across each one of the resistors, and that's going to equal to the total value of the voltage that is supplied to the circuit. So in order for us to find the voltage drop across the resistors, say we find the current that's going to flow through them. All right. So the first resistor is going to observe or say resist the current flow through the circuit. Right. As we calculated earlier, that value was 0.017 amps. All right. So that 0.017 amps times 220 ohms would yield roughly 3.7 volts. All right. So voltage, say resistance time current equal voltage. Right. So the 5 volts that is supplied across the source is lost just as it approaches a 220 ohms resistor. Right. So the differential loss is actually 3.7. All right, so we have remaining 1.3 in the circuit, right? And that now we're gonna share between the resistors and the series parallel section. All right, so that value now is going to reach the first nodal point. So that would have been roughly 1.3. All right, so that 1.3 differential across 100 volts is going to be constant, and then it's going to actually be constant across the 100 ohms and the 220 ohms. So the value of the resistance across the 100 ohms and the 200 ohms will see the same voltage as the value of the resistance on the branch where the 100 ohms is. All right, so these two resistors on the right side of 100 ohms and 220 ohms, we'll see 1.3 or 1.9 volts. All right, because I say that the voltage across a parallel circuit would have been the same. Now, if we should acknowledge that the resistors on the right sides are in series, that value would have been one, sorry, that value or those resistors rather would have to share the value of the voltage, because in a series circuit, the value of the voltage is add up or adds up, right? So look at this now. Say if the value is adds up, that means the two resistors on the right side of 100 and 200 ohms would have different value. All right. So in order to analyze the value of the voltage going through those resistors, all we have to do is find the current. All right. So we're going to find the current across a 420 ohms plus a 100 ohms resistor. In order to do that, we take the total value of the resistor, we divide by the voltage that's supplied across that portion of the circuit, which is 1.3. And that will yield within this parallel series component 4.2 milliamps. All right. Let me say the series section of the parallel component, rather. Even though it's just, I could say parallel series, was series section of the parallel combination. That will have yield for the series section 4.20 milli, or rather 4.02 milliamps. Right? So the next thing we want to do is just find the voltage drop across each one of the resistors. So all we have to do is just times the 4.02 milliamps with the 100 ohms. And that would have given you roughly 402 millivolts. All right. And then if you look at the next resistor, which is 220 ohms, if you should times the value of the current, which is 4.02 milliamps, you'd have get point, or say 884 millivolts, which is roughly 0.884 volts. All right, so that is simple and straightforward. But want you to make sure that you understand how we go about analyzing the value of the voltage within the circuit. All right, and this highlights the relationship between current and the voltage within the circuit. All right, so we cannot overlook what is really happening, because in a real circuit, this is what really happens. We put resistors within the circuit in order for it to limit the value of the current in order to achieve a specific, results. All right, because each component within electronic circuit, they have different value, and those values is what going to determine how these component actually works, right? So the next thing we're going to look at is the values as it's simulated within the circuit. All right. So this is a diagram taken from a circuit that is already simulated. So I'm going to show you now how the whole thing behave within this, or the whole circuit behaves, how the current behave against resistance and the source voltage and so forth. All right. Then I might just go into the real experiment, showing you the ideal resistors that are used and the value of the voltage that is measured across each resistance, right? And the supplied voltage that is placed across the circuit. All right, so all we got to do is just compare the values, and then we're gonna match up back with what is calculated, right? And that should tell us, something from this simple voltage, current, and resistance analysis and our characteristics. All right. So that is just my, tutorial, or rather experimental analysis that I want to demonstrate, right, for this presentation. So guys, stay tuned. Now this is a simulation, a circuit that was shown earlier, and it shows the flow of the current from the source of the 5 volts all the way through the series branch, part of the circuit. So the current moves through the 220 ohms resistors and then down the 100 ohms resistor. It also move across the 100 and the 220 ohms within the series parallel side of the circuit, right? So bear in mind the observation. As the current moves through the series parallel side of the circuit where the 100 and the 200 ohms exists, it actually slows down, and that is due to the resistance on that side of the circuit. All right. But watch on the right or the left hand side how the current moves freely down the 100 ohms resistance circuit. As you can see, the resistance that is offered through those resistors, or the 100 resistor in particular, is much lower than the 100 and the 200 ohms resistor, because the sum of those two actually adds up to 320. All right, so that has a greater resistance, and so it circulates back throughout the circuit, right, from the source. So the voltage recorded from the illustration or the simulation is actually 5 volts, well, from the source end. However, we experience a voltage drop resulted in 1.9, 1.3 volts. All right. So there's a voltage drop experienced by the 220 ohms resistor first encounter by the current within the circuit. All right. So that is roughly 3.7. So that moves down the um the ground portion of the circuit and then return back to the source. All right. Then when it goes to the parallel side, what we observe is that the current slows down. This tells us that majority of the current will flow into the 100 ohms resistor, and as measured it is roughly 12.9. All right, and the current flows through the series parallel section is 4.02. All right, so it can be observed, but it is much calculated better by adding up the two values of resistor divided by the 1.3 volts. All right, so it's adds up mathematically, and by illustration or visual effect you can see that the current, most of it is actually moving through the 100 ohms resistor, because less resistance and less is moved through the 200 and 220 ohms within the series parallel section due to a greater resistance. All right, so greater resistance, less current, less resistance, more current flow. All right, so that is basically the relationship. All right, so let's look deep into this, as we want to understand how the current and the voltage all split up as it moves throughout the circuit. Alright, so we are supplied by a 5-volt power supply from this board here. Alright, so across the input of the circuit we have 5 volts. Alright, and then that voltage is going to split between the first resistor in series. Alright, so we're using 220 volt or ohms rather resistors and 100 resistor. Alright, within the series parallel circuit. So first I want to make sure that you see the values within the circuit. So I'm going to look at the supply voltage, and we're going to show you on the meter, and then we're going to look at the voltage in the series component of the circuit and the parallel side of the circuit. Alright, so we have basically 2 resistors on the far end in series, which is these resistors. These are 2 series resistors, and then this resistor is another resistor that is parallel with these 2 resistors here. Alright, so the value between these 2 resistors, this one is 100, this one is 220. So the value of the voltage between these 2 should equal to the value of the voltage in this one. Alright, so that's a relationship between voltage in series, and this one is in series with the supplied voltage. Alright, so by the time the voltage come across this one, it should experience a voltage drop, right? And then if we should measure the voltage at this point here, it would have been the differential between the voltage across this resistor and the voltage supplied in the circuit by this board, which is 5 volts. So the differential in this voltage is actually 3.7. Alright, so by the time it reached to this one here, it would have leave us with roughly 1.3. Alright, so the voltage going through these or across these 2 here is the value of the voltage differential at this point here. So it is 1.3, roughly 1. It can be 1.29 from my experiment, right? And this one here would have been roughly the total of both, say, the value of the voltage adds up. So the voltage here is 1.29, so these 2 values here would have split the voltage. Alright, and when I work it out, it is roughly 0.884 for the value of the voltage of this 220 ohms resistor, and 0.42 for the value of the voltage for this 100 ohms resistor. Alright, and then we have lost roughly 3.71 here, right, in terms of voltage. Okay, so if we lost 3.71 here, then the differential would have been 1.3 here, or 1.29, and here the value would have been 1.3 across this resistor, and between these 2 it would have been 1.29, 1.3. Alright, so I'm going to be testing across the supply to see the value that is actually sent out. So if I should measure between here and I should measure between here, this would have given me my supply voltage. Alright, so this jumper wire here is adding the value. Alright, so this jumper wire adds the value of the supply. So this will give us the voltage supplied here. So let me switch my meter to DC supply, and that will show you the value is roughly 4.0. All right, so this is what happened now when it comes to this kind of circuit. There's a lot of like losses within the supply. Sometimes we may have poor contact across the jumpers and the resistors and so forth. So my voltage is fluctuating between 4.0 and 4.616362. all right, so the voltage basically is fluctuating. Okay guys, so the last thing that we're going to look at is the voltage across each one of the resistor component. All right, remember that we had checked for the voltage from the supply side, which was roughly 4.7. all right, so as calculated, our voltage across the resistor in series was 3.7. all right, but measured from this experiment, all right, we're gonna have some amount of losses within the circuit, so we can see that the voltage is roughly 3.2, right, and counting. So that's the first resistor across the series component. All right, and that's a voltage loss or drop rather that is measured after the 5 voltage is supplied across the circuit. So we're gonna check the next voltage, which is the differential of the voltage drop from the supply and the one in series. All right, so the value I'm getting is 0.97 or 1.2 or 1.1 roughly, right? So it's roughly fluctuating between 1.14 1.13. all right, remember we calculate it as 1.3, right, or somewhat 1.29 around there. All right, so as again the voltage drop, here's the difference between the supply voltage, right, and the one in series. So that would have given us 1.3, as we measured within this actual circuit is 1.1 1.14. all right, so then let's measure across the two resistors that is in series and parallel against the 100 ohms resistor. All right, so this should have been equivalent to the 1.14 or maybe 1.1. all right, so we're going up, you can see we're climbing to 0.9 roughly. So I'm saying there's drop or both losses within the circuit because we're not 100% in contact within this board or breadboard, so we incur losses within the circuit. all right, so I'm roughly 8.40 8.6 and counting. all right, only if I could have just managed to steady the circuit, then I would be able to maximize on the voltage going across the series component within the parallel side of the circuit. all right, so that is going to show us basically the value as it's the value is not steady because we have losses that's incurred due to the poor contacts within the breadboard and so forth. But then the theory proves itself right. We have the voltage in series and the voltage in parallel. So normally voltage with series circuits adds up, in parallel remain the same. So these two resistors, 100 and the 220 ohms, is in parallel with this 100, and the value for those two resistors is almost the same as the value of the one resistor. All right, so now there's going to be a split between the voltage in series for the 100 ohms and the 220 ohms that is in series within the parallel side. So the voltage is going to split, right? Remember I said them adds up, and it should add up to the differential of the voltage coming across from the voltage in this series circuit here, which is 3.7, and the supply side, which is 5, and that is what, 1.3, right? So this 100 ohms resistor is 1.3 volts, and these two 100 and 220 ohms should have added up to 1.3. Now if we should add the voltage across the 220 ohms and 100 ohms, they should have added up to 1.3. We're just going to check the value though, and we're going to prove that they are going to be equivalent to roughly 1.3, even though we have received almost 1, right? But as we're saying, there's experimental loss that will occur in the circuit. So I'm getting roughly 0.3 on one side, right? That is across the 100 ohms. So I'm getting roughly 0.3, and then I'm going to measure across the 200 ohms. Alright, so I'll make sure so we're able to show it. Alright, so across the 200 ohms we're getting roughly 0.63, or 220 ohms, right? So it's 0.63 or 64 times 0.3. Alright, so we had that value up, we roughly get 0.9, roughly 0.1. Alright, so we'll compare that with our 1.3 value as calculated earlier within the schematic diagram. So I'm just going to check out the second time for the value across 100 ohms. Let's just say the amount of voltage has lost. Alright, so I'm getting 324 millivolts, which is 0.32427, whatever. It's still counting because the circuit, counting up and it's stabilizing. Alright, so that's just basically how the circuit behaves as it pertaining to resistance, current, and voltage. Alright, so we analyze these circuits many a time because we want to know what the values of these components should be. And say for example then we lost one component, we can replace that one with the equivalent value. Alright, say for example some reason we're gonna add something else, it's going to have a different behavior, and then the circuit is going to give us a different results. Right? This could have been something else separate or apart from the resistor, and the specific value that should be obtained would have created some problem based upon the value of the resistor that actually been taken from the circuit. So we have to make sure that the actual values maintained, so the specific outcome can be achieved from a component, right? And this time we're just using resistor just to analyze the behavior within a simple circuit, but this could have been any other circuit. All right, so that is just about it, guys. So next time, and make sure that you subscribe to our platform, give us a like, and you can share that video with a friend or whatever, you know. So that's it. Thank you, take care, have a nice day.